Cool. We officially start. So welcome everyone to the video podcast, A Coffee with Greg Kemnitz. Hi, Greg.
Hi, how are you?
Very good, very good. What about you?
Oh, I'm good. Just enjoying my morning coffee. So here we go.
Can you keep it slightly more far from the camera so we can read? Oh, yes.
Yep.
Fantastic.
Yep.
My cup is an espresso cup, of course.
Yep.
And I don't know if you can see it, but on the
It's
cup,
fully,
you can see
fully Pac-Man. Very nice.
Exactly.
Yep.
It's a gift from a friend who knew I'm a fan of retro computing.
Cool.
So let's start this conversation. And let's start from the most obvious question, probably, because, well, you are obviously a database person who lived with database for all your life. This is well known. I know that people know that because I remember that there was even a question about your background on Quora, which is uncommon. And but your adventure with databases, I think that it started with Postgres, right?
Yeah, I mean, it was interesting. It's like basically how I got started with Postgres was, it happens that my old roommate at Berkeley had been the previous Postgres chief programmer, and he actually wanted to switch to something else, so he was asking me about how to interview for someone to replace him, and he didn't. I was already working in industry by then, but I was kind of bored, and so I said, like, well, why don't I interview? So I went up and had a chat with Professor Stonebreaker, and the rest is history. So he basically said, "You're hired."
Oh, great. How was that experience? And which year was it?
Well, it was like late in 1988. So I was there 89 to 92 is basically the time I was at the Postgres project. And at the time, one of the things that was interesting was Postgres at that time, Postgres was a pure research test bed, and it was based on Ingress, which was Professor Stonebreaker's original big database project. And in fact, it actually recycled a lot of code from Ingress. So, and so basically, when I first got there, that was right the time that one of Postgres's earliest implementations was to actually have a Lisp parser and query optimizer, and the rest was in C. And it was kind of an experiment, because that's what you do with research databases. And it turned out that experiment didn't work. So right when I got there, the team was in the process of de-Lispifying it and going to an all C world. But one of the things that's kind of interesting is it's still the case that a lot of the core data structures in Postgres are basically Lisp S expressions. And that's basically because a lot of the code that worked on Lisp S expressions was already there, so it was just most convenient to keep it that way. And so to this day, the optimizer data structures and the parse trees and these kind of things are basically Lisp S expressions.
So interesting.
Yeah.
And do you think Lisp is a good language to write a database nowadays?
Um, I mean, no. I mean, the problem is it's just too freaking slow. Yeah.
Okay.
And database kernels are so sensitive to things like spurious garbage collection and that kind of thing that you just really, if you're a database kernel programmer, you tend to become an extreme control freak because you just have to make sure that everything behaves in a very sane way and that you don't have stuff that just goes night night randomly because like, oh, I'm going to run the garbage collector now. You're
It's funny because, well, of course, it makes a lot of sense to me, but at the same time, I can't refrain from saying when it comes to garbage collection and speed, how about all the databases written in Java?
Yeah, I mean, because most of the Java databases tend to be they're more networky and they don't really do a whole lot with queries. They're more like access the network, pull up the data from their nodes, and then pass it to the application. Like Cassandra is totally like that. It doesn't really. I mean, since it doesn't have joins, there really isn't much that it does in its core backend other than get the data out of its various storage worlds and then pass the data out to the application side, or pass a lot of data between nodes. So there's a whole lot of message passing going on with most of the Java written databases like Cassandra. So, but they don't really do like gnarly, processing of SQL queries with really gross joins and all this kind of thing, which that's where the things like garbage collection and just general throughput of the language itself tends to bite you if you don't have it. So like, and one of the things that's interesting is in Cassandra world, there's a version of Cassandra that is written in C++ that is also used, and that they did it for exactly that reason, that even though Cassandra isn't quite as sensitive to that kind of thing as a SQL database would be, it's still somewhat sensitive. So
yeah. Well, anyway, do you want to tell us a bit more about what you developed in the Postgres days?
Yeah. I mean, one of the things that was basically my job at the university Postgres was, the grad students would do their whatever they were doing for their research, and that in Professor Stonebreaker's world that involved writing a whole lot of code, and some of the code was good, some of it was sort of not so good, and some of it kind of messed up stuff that we needed to be supported until that research result was known and the person wrote their paper. And so I had kind of a triage job, which is basically, did this stuff work? Is this stuff useful and can be fixed? And if it is, then figure out how to fix it. And sometimes this stuff is not useful. Let's rip it out. Yeah. So that was kind of, and then writing a lot of utility stuff that grad students generally wouldn't really want to be dealing with, like writing test harnesses and doing tests, and because one of the things that the Postgres project tried very hard to do was to support at least some external users, which is pretty rare for university research projects. And so we actually tried to support them as well as just say, here's the code, have fun. which is often a lot of research projects tend to do that, and their code their code obviously doesn't have installers and that kind of thing. And so I wrote a whole lot of that kind of stuff. Plus, occasionally I got involved with research, which was most of the stuff I got involved with was benchmarking and performance analysis.
Okay.
And so I would do a whole lot of setting up the runs, doing the actual running, assembling all the numbers, and then trying to figure out why it did what it did as far as where it spent time in the kernel, so we could write it up in as papers and publish it. So
okay.
So yeah, and so there were lots of interesting tales in university Postgres. One of my favorite ones is why is Postgres called object relational, and where did object relational come from?
Yeah.
And originally Postgres was called extended relational. And if you look in the original Postgres papers, you'll see references to extended relational. And that changed right around 1990. And it actually changed because Professor Stonebreaker went to Washington and met with the various people that give funding, mostly at DARPA and the US military, frankly. And basically he said, objects, everybody wants objects. No one wants relational, it's boring. So I need something to kind of tie it all together. And so he came back and we said, well, extended relational is now object relational. And so it turned out, fortunately, we already had what are now called extensions in Postgres. And so, and extended, you could extend your own data types and that kind of thing. And that existed even in the university Postgres, and was one of the key ideas of Postgres as a thing. And so basically we already were not that far from being able to claim as being an object-based thing. So we added methods and added OIDs and added in table inheritance, and between that and what we already had with the query rewrite rule system and the Postgres extensions and extensible data types, it meant that we actually could claim to be object, and so object relational was born.
Interesting.
Yeah.
I think that nowadays they stress much more the relational part and much less the object part, right?
Yeah, except the big thing that is a huge part of the Postgres world is extensions, and that and the extensions fit into the relational framework very nicely. But they got rid of a lot. The PostgreSQL world got rid of some of the stuff that was there that was kind of hard to support. And I'll admit, if I were them, I probably would have gotten rid of it too. But but yeah, it's like a lot of the complicated stuff is just rarely used in real life. It was more like it looked good in demos, but yeah.
Yeah. To be honest, well, I'm not a Postgres person, but I touched it sometimes, and I think I've never seen people using table inheritance, to be honest.
Yeah, because part of it is if you're a boring DBA type, it's like, what do you do with this thing? What good is it?
Oh yeah.
Because it mostly ends up just being a pain, kind of like it feels like a big mess of triggers and that kind of thing, and you just really don't want to have to deal with it in your production environment, because it might randomly do something bad, which if you're a DBA in a big production system, you don't like stuff like that. So yeah.
Got
Yeah. Go ahead.
No, sorry, I interrupted.
I guess another interesting thing is the history of the vacuum cleaner. And the vacuum cleaner is, I was sort of ripping on garbage collection, and Postgres has a garbage collector. It's a storage garbage collector called the vacuum cleaner, and it's the bane of most DBA's existence in the Postgres world, because a whole lot of your life as a DBA is when to run the vacuum cleaner. Do I use auto vacuum? Do I not? How does that work? And so the vacuum cleaner, originally Postgres, one of the research things that Postgres had, and a grad student by the name of Kurt Collison, who's a buddy of mine, he was working on a storage archiver, and so we actually had this big thing that wrote to worm drives, and someone gave it to the Postgres project to play with, and it was this big messy thing that almost looked like a small version of the rig they had in Rogue One and Star Wars, where they had all this big array of storage things, and our heroes in Rogue One had to find the right one and get it, and upload things to the rebel fleet that was orbiting, because that had the plans to the Death Star on it. So and this thing they gave us looked a lot like that, and even had this robot arm that would go and find these big platters and stick them on a reader. And so one of the things that we had there was, we were trying to archive. Postgres had something called time travel in those days, where you could query it and see the state of all the changes to a row over time. And to support time travel, it meant it had a kind of base table, and then deltas was kind of how the Postgres storage structures worked. And that meant that over time you accumulated deltas, and it meant that sometimes in an operational database, you don't really care about the deltas. You want them to just go away. And but in those times you could also archive them, and that was what the original vacuum cleaner actually did. Was it found all the deltas and then archived them, and then recalculated the base row and wrote that thing. And so basically, it was not originally intended to be a storage garbage collector, but that's what it became. So
it's a pity that it doesn't archive anymore.
Yeah, I mean, they kind of, the PostgreSQL guys, PostgreSQL, I guess I should call it, but yeah, the PostgreSQL team got rid of that, a few years ago, and I think it was basically just it was another thing that was probably not very popular and was pretty hard to support. Because one of the things that we never figured out very well was how do you do indexes on the archive data and stuff like that. So most of the time when you actually did time travel, it couldn't really use indexes very well, because the indexes all wanted to be on a row. They didn't know about versions of the row in an index, although Kurt wrote a paper about how to do it, but he wasn't able to get the code done before he graduated. So but yeah.
I see. I see. Actually, you mentioned the pronunciation. So, what is the official pronunciation actually?
I think, well, Postgres is just Postgres, but the PostgreSQL, the official pronunciation is usually SQL, but I guess one of the interesting bits of history is, Americans are lazy, so we tend to want to drop syllables. And also a more real reason is that was actually the original name of SQL was actually SQL at IBM, and in the early days, and because the original name was let's see, structured English query language. That was actually the original name of SQL.
English, right?
Yeah,
makes sense.
So
actually,
it's SEQUEL, and but it turned out that someone in the UK had copyrighted the name SEQUEL. So IBM's lawyers said you have to change the name, and so they dropped the English part, and it became SQL.
Interesting.
Yeah.
Well, I noticed that different database communities use a different pronunciation. So, for example, people who work with SQL Server call it SQL Server, but the creators of MySQL say MySQL. So I tended to adapt to each community's standards.
Yeah, and that definitely, like, I will admit I have to be careful with the MySQL people, because my instinct is to just say MySQL, because, well, that's 3 syllables instead of 4, but yeah.
Nowadays, everyone says MySQL, but not the creators.
Oh, yeah. I mean, one thing is, there definitely is a thing of, it seems to be, if English isn't your native or original language, you tend to spell out the letters, whereas so, like, because obviously MySQL came from Northern Europe and in Finland, Sweden, and those kind of places, and so, like, and whereas, like, Microsoft is obviously from Washington, and it's SQL ended up being SQL Server, and even in the US you have, like, Oracle people tend to want to call it SQL, but and in fact, in Oracle's official documentation, it says this is pronounced SQL, but but there's still a weird tension between the SQL camp and the SQL camp. So
Well, as an Italian, I remember a time where people translated the acronym, so they said funny things like PostgreSQL. So they mixed the right prefix and then the Italianized acronym.
Yeah, I mean, I met French people that call it Squill. Yeah, they kind of try to shorten it that way too. Yeah,
makes sense.
So my Squill or Squill server. So yeah. Yeah.
Well, a friend of mine who's obviously not a technical people occasionally asks me things like, what are you doing with your gits and squirrels?
Yeah. Oh, wow. Yeah.
Well, anyway, back to Postgres. Let me move to an uncomfortable question. Back in the days you were talking about, obviously, you guys made a lot of design decisions that obviously made sense back then. But do you think that all of them should be revised now?
Well, I mean, one of the things, there are kind of several things, if I was you were going to build Postgres today, what would you do differently? Like a big one would be, it would have a much more modern thready process model. Like, because the Postgres basically just inherited the Ingress process model. And in those days, people didn't really understand threading very well because, their threads were, OS threads existed, but there wasn't a lot of OS infrastructure for user level threading in the 1970s and early 1980s. So basically Postgres became a multi-process model, and as was Ingress, and they all have and as it happens, Oracle has the same process model because it's from the same era. So basically they all have the notion that you connect to some kind of a dispatcher process, and that thing figures out if there's any idle processes lying around for you to connect to, and if there is, then it connects you to that thing. Otherwise, it forks up a new one and connects you to that. And basically, in Postgres they call it a postmaster. In Oracle they call it a listener, and I actually forgot what they called it in Ingress, but Ingress had one too. And and if you go that way, that means it mandates a bunch of things. It means all your shared stuff has to be explicitly in shared memory, and you also have to use shared semaphores to do coordination, and these things tend to be somewhat heavier weight than just doing stuff inside of a multi-threaded environment where you can just coordinate. You just have a pool of memory that all the threads look at, and you just have to make sure your semaphoring and your critical section handling is correct. But otherwise, it's just, you don't need any special OS support to support that kind of thing. And plus, it means instantiating a connection from an application is far faster in that environment than it is if it's having to possibly fork a whole new instance of the back end for you to connect to. So yeah. So in MySQL, if you're connecting, it takes maybe a few microseconds to establish a database connection, whereas in Postgres it can take up to a few hundred microseconds to get a connection because it has to wait for things to fork and stuff. So yeah. So that would be something, if I was going to do it today, I would definitely have a more thready approach as opposed to a more process heavy approach.
Okay.
And then another one would be, the Postgres storage engine is a very good one, and it's a testament to how good it was done, with that it really hasn't changed enormously since the university days. The high level stuff is all still there, including the vacuum cleaner. And if you're going to do a Postgres storage engine today, you would not have an explicit garbage collector because they suck. They're just a headache for DBAs to figure out. So you would just write your versioning and that kind of thing would just be handled by the implementation of the storage engine itself, and you would plus you would not ever worry about trying to do time travel. So because often this kind of stuff ends up being baggage that just keeps being dragged forward because no one wants to go through all the pain of rewriting it and possibly breaking a whole lot of existing user code in user storage. So yeah. So that
if you could go back in time, would you suggest doing a physical raw version as Postgres does now, or would you suggest in-place updates with transaction logs like MySQL?
I would probably do in-place updates with a redo log, since that was a design that even when Postgres was being done, like things like SystemR actually had those, at the time. SystemR was IBM's research database that was around the same time as Ingress. So having a redo log or transaction log and in-place update tends to simplify a whole lot of problems. And it means, like, because one of the things that is a thing is, do you optimize for a successful commit, or do you optimize for rollback? And pretty much the guiding wisdom has been that rollbacks are very rare and should almost never happen. So you should be optimizing for successful commit in the innards of your storage engine, and just say, if a rollback happens, it just has to walk the rollback log and fix the storage, as opposed to trying to optimize for a fast rollback and do it that way. So so definitely, in-place update is a very good thing, but you do need to make sure that your redo log has all the machinery needed to fix it if you do need to roll back. So
one of the reasons why I like to talk with you is that I can talk about these kind of things without being treated like an idiot. I mean, historically, the Postgres community is not very good at accepting criticism. And I love criticism because, criticism helps technologies to improve. Every technology needs criticism, in my opinion.
Right. Well, certainly. One of the things is whether you like it or not, the simple existence of competitors is an implied criticism of the other competitors just by their very existence, and the fact that they do things different. And occasionally they get competitive advantage because they did something that you didn't, and it made their little thingy better than yours. So go ahead.
No, it's true. But apart from that, unless technology is absolutely perfect, which is impossible, it needs criticism, or it won't improve.
Well, and especially something that's been around for long enough that certainly everybody who touched the Postgres kernel at the university is not far from retirement age now, if not actually retired. So, when something has been around that long, there's a whole lot of legacy cruft that is just kind of dragged forward. No matter how clever they were, they couldn't anticipate changes to technology. And like, one of the things that I always like to try to point out is, like when I was at Postgres, one of the things I had to do was, we got a new hard disk for our VAXs. Our main Postgres servers were VAX 11780s, and they're big. I don't know if you've ever seen a VAX, but they're big refrigerator-sized things that are what they used to call mini computers, and it wasn't anything very mini about that thing, but basically, it's hard drive. We got a new hard drive, and we we're going to put it in there, and the hard drive was basically about the size of a dining room table, and it weighed probably about 200 kilos. And so it took like 4 grad students and me to sort of manhandle this thing into the slot and shove it in there. So, and it was all of 500 megabytes. So yeah.
Oh yeah.
Yeah. And that was a big enterprise grade thing that cost several tens of thousands in 1989 money. So yeah. So basically it cost as much as a really good car. So yeah. and that was the world that Postgres originally came from, was that world where the computers were like thousands of times slower than they are now, and RAM was thousands of times more expensive. And so you designed your stuff around those kind of high level requirements. And modern computers have way different requirements. And so that's why I say, like, if you're going to design a database engine today, one of the big things is you would probably use GPUs a lot more. Like, obviously GPUs were, and frankly, most of NVIDIA's engineering staff didn't even exist yet. So, and so we had no clue that there were going to be things called GPUs at the time. But database engine can make a lot of use of GPUs if they're there, and because they let you do insane levels of parallelism and let you do all kinds of things that are harder to do in just a normal traditional computer, where it is still the case that threads and sequential processing is still a somewhat heavyweight activity. Whereas like I can just like one of the things you could do with GPUs is you could say things like, here query optimizer, why don't you give me 1,000 plans and figure out which one's the best one, and evaluate each plan on like a GPU thingy. So you could do stuff like that now that you couldn't even imagine doing in those days. So so sorry, I was rambling, but go ahead.
No, it's these are interesting thoughts. Okay, let's do a big jump in time, and let's go to what you're doing nowadays. Do you want to tell us a bit about Wirekite?
Oh, yeah, definitely. Wirekite is my startup. My partner Tarun Sandhu and I are working on it, and it's inspired by a project we had at Google where we migrated about 1.5 petabytes of stuff from MySQL into Spanner, and that project was actually finished after we left, but we started it and we wrote the code for it, and we realized even though data migration is a pretty well understood thing that has been around as a need for ever since databases have existed, it tends not to be done very well. So because it tends to be very ad hoc and improvised, and a lot of the existing data migration tools are pretty slow and not really optimized for large scale production worlds very, very well. And so because one of the things we did at Google was we sort of surveyed the landscape of the data migration and realized like most of these tools are really slow and also tend to be frankly consultantware that requires you to hire some expensive guy to come in with dragging his laptop to sit in your office for 2 weeks, and that guy will charge you a few tens of thousands of bucks to set things up for you. And so those two things we realized like we really don't like that. So we've been working on Wirekite to sort of try to be really fast and really easy to deploy in production environments. And so basically, we support the big five databases, SQL Server, MySQL, Postgres, Oracle, and MariaDB, and we're actually also working on support for Cassandra as a data source, and we target all of those, except we probably won't target Cassandra, but we target all of the other guys, and we also target the usual cloud suspects like Snowflake and Databricks and BigQuery and Spanner and Single Store and TigerDB. So, so basically, Wirekite works in on-premise and cloud and in combinations of them. So like you can extract your data from an on-prem environment into a cloud target, and that kind of thing works too. And we support data extraction, which is kind of just dumping the current data set, and we also support change extraction or change data capture using whatever is the most native thing that the database supports. And sometimes some databases we actually support multiple change data capture schemes, because some of them have really good change data capture schemes if you can actually run Wirekite on the same physical server as the host, because then we can read the logs stuff. And but sometimes if you're in the cloud, you can't do that. So then we use the API, the CDC APIs that the database vendor supports for remote access to the CDC, and when we support multiple methods when they're appropriate. So and we also have what we call target sync, which allows for if you don't want to set up the full machinery of change data capture, you might just want to like sync two databases together, maybe once every n hours or whatever. And target sync is a mechanism to let you do that, so that you can just boot it up, it figures out the diffs, and then synchronizes the target with the source. And one of the other things we're working on is a language for describing changes, and that's still being kind of in heavy research mode. But yeah, so we're doing a soft launch very soon, and we also are working with MariaDB, because one of the things is, we're working with the MariaDB organization, and we're a MariaDB Foundation Silver sponsor. So, and we will be, presenting to the MariaDB world fairly soon. So
interesting.
Yeah.
Interesting. I can't wait to try it, actually.
And one of the things that we're kind of proud of is we did a SQL Server. One of the things we also support is we actually can stream changes to things like Kafka or Red Panda. And so like we don't just stream to databases, we also stream to queues, and a lot of users want to actually process the changes using a queuing system in their apps, because they want to do complicated stuff with the changes that is beyond the scope of what you would normally do with SQL or whatever. But so we support that also, and our marquee thing was Postgres to Firebolt, and that we got 430,000 changes per second. And And so, we definitely, and Firebolt is one of the targets we support that is a really super fast target. So yeah. Yeah.
Do you also support filtering of events, like by table or by column? I don't know.
Can you restate that?
Yeah, sorry. Can you replicate changes for just some tables if you need to?
Oh, definitely. Yeah,
Okay.
I mean, because basically you just tell us the tables you want tracked, and we replicate those. So you don't have to track your entire database.
Okay.
Yeah. So yeah.
And can you also skip columns containing private data, for example?
At the second, we don't actually do columnar filtering, but it usually, so yeah. So usually we do table level stuff, and we're certainly going to be doing extensions as they become interesting. So yeah. And one of the things we try hard to do is, there's a kind of debate in doing change data capture between, do you want to go fast, or do you want to make it super configurable and super customizable? And our bias has been to make it really fast, frankly, because there definitely is a pretty big engineering trade-off between the two.
Okay.
Yeah.
Yeah, makes sense. Okay, I'm curious about some things. For example, you said that existing tools are slow. Well, obviously, I agree. But and you say that Wirekite is faster. So, what makes it faster than existing tools?
Well, one of the big technical things is a whole lot of these tools use queues as their mechanism for connecting sources and targets. So basically, like their source extractor will write records into a queue, like Kafka or something, and then the extractor will read the queue, and that does solve a lot of engineering headaches for you. But the problem is the queue is an intermediate layer and adds its own overhead to the mechanism of transferring your changes from one side to the other. We tried to keep it really simple, and we frankly just use disk files and use an intermediate format to transfer the data from one side to the other. And so basically, there's a lot less machinery in the way, and that helps to make us a whole lot faster than a lot of these other guys. So yeah.
Okay.
Yep. And we do crash recovery very carefully and around our stuff. So like, you can kill and restart or have the machine crash that is running our change extractors and our CDC pipelines, and they'll just heal and recover and restart automatically on their own. So yep. So yeah.
Do you plan to open source it or part of it?
That we really don't know yet. I mean, one of the things that's a bit tricky in the world of open source for something that is this specific is, like, you've given away all your secret sauce, that, like, because like it basically implies a very different business model of one that's very consultant heavy, as opposed to trying to actually sell stuff, frankly. And and we haven't really decided yet on the direction we're going to go with that. And initially, it isn't open sourced, but we shall see. Yeah.
Since you mentioned this problem of the giving away your secret sauce, I'd like to ask your opinion about something. You know that in recent years, a lot of databases moved away from the open source licenses or moved to AGPL, which is open source, but basically it states that if you modify the code and you provide it as a service, you need to publish your changes, which is clearly a move against cloud providers, because cloud providers fork open source projects, they sell them, and the original vendors basically don't have any interest in this.
And that is one of the things. Yeah.
I was just curious. I mean, I'm not asking if you're going to do that. I'm just curious, what do you think about these kind of moves? Because, people are split, right? Some people are critic about this, others say it's acceptable.
And I guess one of the things I'll just say up front is everybody has to eat. No one writes code for free, truly for free, just as a sort of art project. Yeah. Eventually they want to somehow make a living as software engineers in one way or another. Yeah. Either by selling a product or by selling their consulting services or somehow, or maybe getting honoraria by talking at conferences or something. Yeah, they have bills to pay and they got to get money to pay them. So my own feeling is, one of the things that's tricky about the cloud world is the cloud providers, they really don't care about software. They just care about you running stuff on their cloud. They don't care if it's Oracle or Postgres or any other thing. If it generates cloud fees and needs compute and needs storage, they're going to make money. And so in a way it's good for the community, because it means they aren't going to favor anything or particularly favor their in-house stuff versus others. That if you want to have a managed Postgres, they'll happily manage it for you, and you'll pay the cloud fees for it. Whereas so like Amazon doesn't really care whether you use RDS or you use a self-managed Postgres, because they're going to make AWS is going to make its money off of it. So so one of the things that's tricky is ironically in a lot of the open source stuff, the cloud guys will just get it and use it and then package it and sell it. And it's very hard to stop them from doing that, because they're not really selling the software. They're selling they're really renting you their cloud, and they don't really care about what software you run or where it came from, or is it your software, or and they don't even really if you write the licenses strict enough, you can basically forbid cloud people from using it, but that's really hard to enforce, especially if someone has a self-managed thing in the cloud. Like it's not AWS that stuck that thing in the cloud, you did it. So
Right.
So I don't know if I helped to answer the question, but that's kind of one of my general takes on the in a way it means there's a lot less traditional licensed software these days, but I still think there's some areas where you kind of it makes sense to be more a traditionally structured thing, especially if there actually is IP that you frankly want to make money from for a while until everybody figures out what you're doing, which eventually they will. But yeah, but yeah.
Okay. We're approaching a hour of length, so we should stop. But before we end this podcast, I'd like to ask you two quick questions. Which language you're using for the project, and if you're using AI, and how?
Well, we're using a mix of Golang and C, and because some especially some of the CDCs work best in C. So in those situations we're using C, but our kind of default language is Golang, because we kind of learned to use it and got good at it at Google. So it's kind of the language, until we see a need to not use it, we use Golang. And we definitely make heavy use of AIs for helping us, one of the things that AIs are really good at is figuring out like how arcane API things work, and things that would take you a couple of weeks of reading bad documentation, like the AIs will just go and figure out for you and say, this works, and it'll keep probing and generating code and keep trying until it's figured out how the API actually functions. And that's something that I really like about using AIs, because having had to do that in the pre-AI days and figure out protocols and figure out layouts and this kind of thing, it was a huge pain in the posterior before. So yeah, and so we definitely use AIs for that kind of thing, plus helping us with our test infrastructure, because we have a pretty big, we probably have as much code for tests and test infrastructure and test harnesses and things as we do our actual product. So and AIs help a lot with test coverage and running tests, debugging why tests fail. This kind of thing is kind of in, AIs are really awesome at digging through vast amounts of logs in literally superhuman speed. And so when a test fails, you just tell the AI to go and dig around on logs, and after a minute or two, it'll say, oh, this is the problem. Here it is. And very occasionally it's wrong, but about 99% of the time it's right. So, and sometimes you just have to say, that can't be true. That thing was always, and AI is, one of the funny things is sometimes AIs get lazy. Like they'll say, you know what, 99% of the tests pass. I think we're done. And I have to say, it's a database. The data all has to be correct. The 100% of the tests have to work. So, or it'll say, oh, that was a spurious failure. Or, sometimes it sounds like a smart engineer who's been working for 6 months. He'll try to say, you know what, the test worked before and now it's failing. That's just a spurious failure. Maybe I can ignore it.
Yeah. Well, I think it was a great conversation, and I thank you for this. And to be honest, if we had more time, I would ask many more questions. But of course, we can't talk forever. So I hope to have you again when you do the launch of Wirekite. And then we can talk more about it, and maybe you can even give us a demo, and maybe we can talk about the copies the topic that we couldn't cover now.
Yeah, cool.
Yeah.
Okay,
Well,
cool.
So
be
best wishes with your project.
Thank you.
And I hope to talk to you soon again with another Coffee with Greg Kemnitz.
Yep, that would be awesome. Thank you.
Great. Thank you, Greg. Thank you, everyone. And bye.
Bye-bye.
Mm.